This is the base. 2, 3, 4, 5, 6. An exponential function has x in the exponent, right? 2 to the x. If I ask you what 2 cubed is, you would go to the base of 2, see how it's bolded, and then you would say, okay, 2 cubed is 8. See how that says what power you're talking about? So if I asked you what is 8 cubed on this table, you go to the power of 8. This is 8 squared. This right here is 8 cubed, 512. So that way you can see, without having to use your calculator, how some of the numbers are related to each other. The other thing we're going to talk about is what a negative exponent does. A negative exponent just gives you the reciprocal of the positive exponent. So if you had, 3 squared is 9, what's 3 to the negative second power? 1/9. So you see how you've got a 9 on this side and a 1/9 on this side? So if you can figure out what power family you belong to, it helps you with solving exponential equations. So for example, if I ask you, what does the number 625, what power family does it belong to? You would say it belongs to the power family of 5. It's a power of 5. But if I ask you the number 75, 75 is not a power of 5. Because 5 squared is 25 and 5 cubed is 125. 75 is not in the power family of 5. So these are called power families. So instead of you typing them all into your calculator, you could go back to this table and look at power families. So I'd like you to take a couple minutes on your own and take a look at the different power families and see if you can answer the questions down here at the bottom. Do you see any patterns? What do you notice about the power of 0? What do you notice about negative exponent powers? We just talked about number 3. And give examples of numbers that are members of more than one power family. So take a couple minutes kind of as a warm-up. If you've already done it, great. If not, take a couple minutes and see if you can come up with some patterns and kind of look at the numbers in the different power families. Yeah, I actually only noticed that there was a 5, but Killian noticed that any of the powers of 5 happen to end in a 25. So that might help you because, like we said, the number 75, you might think, is 75 a power of 5? It's not. It doesn't end in a 2-5. So that's a good pattern to observe. Did you notice anything about powers of 6? They always end in 6. Because if you're multiplying a number times 6 and it already ends in 6, 6 times 6 for the ones will always be another 36, right? So 6, if it's not a power, if it doesn't end in 6, it can't be a power of 6. Did you notice any more patterns? Oh, I didn't notice that. 3971, 3971. Huh, that's interesting. I didn't notice that one. 4? Oh, I didn't notice that one either. 4, 6, 4, 6. Yeah, that's good. All good patterns to observe. And I wanted you to notice with negative, the pattern is that these are the reciprocals. I think I asked about that separate though, right? The power of 0 is always what? Power of 0 is always equal to 1. And if you forget that, if you type it into a calculator, that's always a good thing to do if you got a calculator. So if I type in like 9 raised to the 0 power, my calculator will tell me 1. 567 raised to the 0 power, my calculator will tell me 1. If I did 1/2 to the 0 power, 1. So anything to the 0 power is 1. So that's an important property that we're going to learn today. I want to show you something though in the table. We said exponential is multiplying by a certain number every time. So the powers of 2, you're multiplying by 2 to get to the next number. 3, you're multiplying by 3 to get to the next number. How do I go backwards in a table? If I'm multiplying by 2 in this direction, I would divide by 2 to go backwards, right? 8 divided by 2 is 4. 4 divided by 2 is 2. What's 2 divided by 2? 1. 125 divided by 5. 25 divided by 5. What's 5 divided by 5? 1. So in order to make this table pattern hold all the way across, that's why all the 0 powers have to be 1. Because what if these all were 0? Well, then I couldn't get to this side of the table because 0 divided by anything would be 0. So this has to be 1 to hold the pattern all the way across the table. And the negative exponent power is always the reciprocal. Reciprocal. So if I go over here in the powers of 9, 81 and 1 over 81. 729 and 1 over 729. What do you have to see? It's the word reciprocal? Yes. Reciprocal just means flip it over, make it a fraction, so it's 1 over the number. And then give me some examples of a number that shows up in multiple power families. So as I look up here, do you see the number 16 showing up anywhere else? Yes. So I see it here again, right? So 16 shows up in 2 different power families. So you could say 16 is a power of 2 and of 4. Give me another example. Something else that shows up more than once. 64. 64 actually shows up as a power of 2, a power of 4, and a power of 8. 64 is power of 2, 4, and 8. Did you find another one up there? 81. Okay, 81. What 2 power families does that show up in? 1. 1? You mean 3? 3 and 9. So it's going to be helpful for us in a couple lessons when we need to look for a common base. 81 is a power of, what do we say, 3 and 9. So looking for things in common across power families is going to be important. Does 49 show up anywhere else, for example? No. So 49 is only going to be a power of 7. The next power family it would show up in is the power family of 49, right? 49 to the first power. So we're going to look for ones that have things in common. You should know like these without a calculator. This is okay. I don't know this number cubed. So, like, you should be able to square any of the numbers from 1 to 10. Those are up here on the board if you get lost. But you should know 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. I personally don't know 6 cubed, 7 cubed, 8 cubed, or 9 cubed, so those would be calculator questions. Why should you be able to do 10 to any power? 10 to any power. I should be able to do 10 to the 8th. That's just a 1 with 8 zeros, right? 10 squared is just a 1 with 2 zeros. So you should be able to do any power of 10 without a calculator. That's another pattern that we could add on there. All right, so power families. Skip now to page, resource page. The resource page 4.3. Was anyone not here yesterday? I was before. I think this is too much to memorize. So I'm going to show you the strategy of if you can't remember, how can you figure it out without having the rule memorized? That's what this repeated multiplication step is for. It'd be nice if you had the general rule memorized, but there's 6 rules on here. So you don't have to memorize them. You can use this strategy of repeated multiplication. The first thing I want you to notice, the base has to be the same. These are both x's. If I have an x and a y, I can't use this simplification. So see how down here, they both have to be the same base. They both have to be a y, or they both have to be a z. Okay, so repeated multiplication, x to the 5th would look like this. X, times x to the cubed would look like this. X. So that's really how many x's that are being multiplied all together. 1, 2, 3, 4, 5, 6, 7, 8, right? Because this multiplication symbol isn't any more important than the multiplication symbol that I can't see here, right? X times x. Right? Multiplication is commutative. You can do it in any order. So this is really x times x 8 times. So it's really x to the 8th power. See how I can count them up? and I get x to the 8th power. What's my rule then? Shortcut rule. What did I do to the 5 and the 3? I added. So if you can memorize that you just add them together, that is the shortcut rule. But the base has to be the same, and then you add the exponents. If you can't remember that, this is a quick way to check the rule. X is x to the 8th. So it says the product rule is to multiply powers with the same base, you add the exponents. You shouldn't have to memorize that. You could literally write out repeated multiplication and you'd get the same answer. Quotient rule. You also don't have to know the name of the rule. I don't care if this is called product rule. Doesn't matter. As long as when you see this on an example, you can simplify it and write this is equal to x to the 8th. You don't have to know the name of the rule. Quotient rule. Now I'm dividing. X to the 4th divided by x cubed. Let's write out what this would look like. X in the numerator, x in the denominator. So, what is anything divided by itself? This x could cancel with this x. Same thing with the second one, and same thing with the third one. So anything that has a partner, top and bottom, can cancel out. Anything divided by itself is 1. What am I left with? X. Or I could write x to the 1st power. Maybe that would help you see it. So why is that? What did I do to my 4 and my 3? I canceled, but what's the rule? I'm subtracting 4 minus 3 to get 1. So my general rule is take n and subtract m. But you don't have to memorize it. You write it out as repeated multiplication, cancel it, but it is subtract. So to divide powers, you subtract the exponent. But it has to have the same base. So if you had x to the 5th over y to the 8th, you can't simplify that. X and y can't be combined together. There's like 2 different variables. Raise your hand. Have you seen these before? Algebra 1A, 1B, or middle school? Okay, so these rules, they seem like I've seen it before, even if I forgot it, maybe. It seems kind of familiar. So that's good. Second time around, I feel like it's always easier. I don't know if you've seen the power rule before. The power rule is a third rule. So once you have 3 rules, it starts to get scrambled in your brain. You may want to write out repeated multiplication to check what's going on. I'm taking x squared and I'm multiplying it by itself 3 times. So I'm really multiplying x squared times x squared times x squared. That's what x squared cubed means. How can I write that out with repeated multiplication? X is how many x's being multiplied? 6. 1, 2, 3, 4, 5, 6. That's what x squared cubed looks like. Tell me what the rule is then. How can I go from this exponent to this? What did I just do? So when you distribute, you multiply the exponents together. So our first rule was add, our second rule was subtract, and now our third rule is multiply. I would always rely on this if you're unsure. You can always check if you have the right answer. You multiply. So when you distribute a power to another power, you multiply. Those are the 3 big rules that you have to keep separate in your brain. To me, those are the 3 that students kind of get confused and forget about, so I always recommend repeated multiplication. The distributive power, this should kind of make sense because most of you already know the distributive property, right? If you have something outside a parenthesis, you have to distribute it to every single thing inside the parenthesis. So if I distribute this n, I would have a to the n, and I also have times b to the n. So everybody inside gets the power. Same thing on the next one. I would get 3 squared because the 3 gets the exponent, and I would have x to the 6th because the x cubed also gets the exponent, better known as 9x to the 6th. This is the guy that usually gets forgotten right here. A lot of times people will just say this is 3x to the 6th. Every single term gets the exponent. So don't leave anybody out because you'll have the wrong answer. And if you're unsure, this squared would be 3x cubed times 3x cubed, right? So it makes sense that the answer is 3 times 3 is 9x to the 6th, because you're multiplying the number times itself. So if you aren't sure if you should distribute the squared symbol, write out the whole thing in repeated multiplication to see if you get the answer. Same thing for quotients. You would distribute the n, so you'd have a to the n over b to the n on top and bottom. What would be my last one? How do I distribute this guy? X to the 6th over, yep. So you multiply the exponents because you're distributing them. So distributive power rule, if an exponent is applied to a single term in parentheses, the exponent must be distributed to every part of the term. That's just the normal distributive property. To me, that one doesn't really take memorization of any rules. You're just, everybody gets it. The first 3 are the biggies. Okay. These next 2 we just talked about in the table of powers. I'm just going to prove to you why. Why do we have this negative exponent rule making it a reciprocal? Why does that make sense? Did someone just make that up? So the negative exponent rule is that you are allowed to move the number down into the denominator, it becomes the reciprocal. So why is that? So I'm going to show you this next example 2 different ways to kind of prove to you where it came from. So it says, first, let's simplify using repeated multiplication and canceling. So let's write this out. A over A. Good thing I didn't pick a bigger number than 3 and 4. You'd be writing like 21 A's over 50 A's. A lot of A's. 3 of them cancel, right? Cancels, cancels, cancels. What do I have left? I have 1 over A because this A is sitting in the denominator. So I want to show that it's sitting in the denominator, and anything divided by itself is not 0. Anything divided by itself is 1. So 1 over A is what I get. Let's use our other rule. Let's simplify using the quotient rule. Do you remember what to do to the exponents for the quotient rule? Subtraction, right? 3 minus 4 is how much? -1. So if this came out from the same original problem and this came out from the same original problem, don't these 2 things have to be equal? So a negative exponent is just the reciprocal of what you have. So I was kind of proving to you, we don't really like writing things with negative exponents, so we're going to practice writing it like that instead. Okay, what would I write 45 to the negative first power as? 1 over 45. So think of this as a sad exponent. You move it to the denominator to make it kind of happy. Now it's a positive first here. I don't have to write the 1. Has anyone seen the negative exponent rule before? This is one that sometimes gets skipped earlier on in math, so this might be the first time you've seen the negative exponent rule. This is 1 over x squared. Because x to the -2, I can move it to the denominator and make it a positive exponent. So when something is raised to a negative power, you
What did I say? Not draw the line. Flip the line? I think you flip the line. And change the sign.
So you're flipping the line because the 45 is on top, now the 45 is under the line. And then I've changed the sign from -2 to 2. So the negative exponent rule, I just need to star for myself, I think, that we need to do negative exponent tomorrow again, because that one is the hardest one, I think. The 0 exponent rule is easy. What's anything to the 0 power? 1. So I wanted to prove to you kind of why. So let's write repeated multiplication again. So what if I have a cubed on top and a cubed on the bottom? What happens when I cancel? Everything gets a partner to cancel with. And anything divided by itself is 1. So this is 1 times 1 times 1 is 1, not 0. What if I use the quotient rule? What's 3 minus 3? A to the 0 power. So if 3 minus 3 is 0, then a to the 0 power must be equal to 1, right? Because I simplified the same fraction using 2 different techniques. So that's why a to the 0 power must be 1. All right, so the two answers down below. 12 to the 0 power is 1, and this whole gobbledygook inside, but it's to the 0 power, so this whole thing is also 1. You don't even have to distribute it. If you've got a parenthesis to the 0 power, it's 1. Anything to the 0 power is 1. Fractional exponent rule, I'm saving till tomorrow. It'll hurt your brain for today. But, you appreciate saving fractions. All right, let me just check. So I want you to do some practice now.